Hi, it's time for some harmonic waves. Let's consider the following waves, defined as functions of sines and cosines, where a and k are just constants. Of course, these two expressions are related by a pi over 2 phase shift, as you learned when you were an even younger Padawan. Notice that we can represent this wave as a function of the position, the wave frozen in time, and we can also represent it as a function of time for a fixed point in space. This equation describes the temporal evolution of all points in space and the spatial distribution for all instants of time. If you have studied Fourier transforms, you shall know that we can represent any periodic function as linear combinations of sines and cosines. This is very convenient, as that way we only need to concentrate in sines and cosines. Because the periodicity of the sine function, the disturbance or intensity of the wave is the same after a full wavelength. Consider a wave frozen in time. So the argument of the sine function, if we move the position by one wavelength, has to be the same. But that also happens if we add 2 pi to the argument. This can be written as a times the sine of kx plus lambda plus vt is equal to a times sine of kx plus vt plus 2 pi. And then we get that k times lambda is 2 pi, so k is proportional to the inverse of the wavelength. K is called the wave number. We can consider the behavior of a single point. Its displacement after a period t will be the same. This can be written as a sine of kx plus vt plus capital T equal to a times sine of kx plus vt plus 2 pi. From where we get that kvt is 2 pi, or using the fact that the period is 1 over the frequency and the fact that k is 2 pi over lambda, then the velocity v is the frequency times the wavelength. Nothing of this should be new to you, just as the relationship between the frequency nu and the angular frequency omega. But let me write these results in one side and use them now to write the equation of the harmonic wave as a sine of kx plus or minus vt, or a sine of 2 pi x over lambda plus or minus t over t, or a sine of kx plus or minus omega t. Of course, where it says sine, you can also write cosine. The argument kx minus omega t is called the phase of the wave. This phase changes but gives the same result periodically. When the sine of the phase gives the same result as before, we can compare and write delta phi equal to k delta x plus or minus v delta t, which is equal to 0. And this leads to delta x over delta t equals to minus or plus v, just confirming that v is the velocity of propagation, where the negative sign corresponds to moving to the right and the positive signs means moving to the left. Let me now write the general form of the harmonic wave, adding an initial phase to account for the initial conditions. Probably now is time to recover those memories from 10th grade when you studied complex numbers, because we can use complex numbers to write a harmonic wave. A complex number is a number formed by a real part and an imaginary part. You might have an imaginary friend, or you might not, but you are going to have imaginary numbers for sure. And the chief of the imaginary numbers is I, which is the square root of -1. A is the real part and B is the imaginary part, we can represent complex numbers on a 2D plane, and the modulus of a complex number, its magnitude, is a squared plus b squared. From this, we can also write that a is z times cosine of theta and b is z times the sine of theta, or a is the modulus of z times the cosine of theta plus I the sine of theta, or modulus of z times the exponential of I theta. Remember that the complex conjugate of z is z star, and it is the same number but changing the sign of the imaginary part. That way, the modulus or absolute value of a complex number is itself multiplied by its complex conjugate. This shall always be a real number. With this at hand, we can now write the harmonic wave.
Yes, we didn't forget we were dealing with harmonic waves.
A harmonic wave can be written as the real or imaginary parts of a times the exponential of I times kx minus omega t for a wave moving to the right. Think about this imaginary old friend and may science be with you.